Okay, so let's get back to this. So we just went over hyperbolic paraboloids. Now we'll talk about the next shape, and remember there's two types of hyperbolic paraboloids, or they're two instantiations of the same geometric shape, whichever way you want to look at it. This is there's in the same token there's two kinds of hyperboloids of a single surface, right? So there's circular and elliptical. So I'm first going to talk about circular. Okay, so circular hyperboloids. By the way, I think the best way to show this would have been this video. I think I figured out what was going on with my videos at the break I took. I think the videos actually got deleted from my computer, so I just have these still things. But the good news is you can go to these websites, and they're in the slides I'm going to get you, and you can see all the videos. These are animated, but really. You can imagine if you have imagine a hard metal ring on the top and bottom here, and they're both on parallel planes, even though admittedly that doesn't look terribly parallel. And say you have taut strings or wires or something. I mean, I guess it's easier to visualize with strings, like it's hanging down there. And you take these two things, and they can be in a cylinder standing straight up, and then you twist them. And you'll see them kind of start producing this kind of shape where it starts necking in the center like this. And then at some point you pinch them off and they become cones. Okay, once you twist it basically pi or 180 degrees, it with respect to each other, it pinches off and becomes two kind of cones. Okay, and so this shape is called a circular hyperboloid. If the two top things were a circle, and of course, as you rotate them, every cross section that's parallel to those circles will be a circle. Okay, and so as you can see here, these are all circles. And then the surfaces, the side contour here, are hyperbolas, which is where the name hyperboloid comes from. And one thing to note right off the bat, obviously, is because at every, whether it's the cylinder or the cone, the surface of that shape and everything in between was made of lines. This is also a ruled surface, as you can imagine. Okay, and I'm about to show you it's also a double ruled surface, although I'm only showing one set of lines. I'm only showing the front here, and then these are just different contours. Here we're showing the hyperbola and the circles. Okay, let's keep going here. Okay, so you'll see the way another way you can think of constructing these, instead of the strings on the two things we twist, you can think of them as they have a central axis up right in the middle of all the circles in the cross section, right up the axis, and you can imagine, say there's a perpendicular rod sticking out from the center. And then there's another rod that's really stiff that has some angle alpha. So say this is some length L out, and on this thing, this if you can see this animation, this central axis would be like this dotted line, and this L bar is this bar that's kind of whipping around here, and then this angled bar would be the blue one with some angle alpha. And as it rotates around, it you can kind of see if it rotated around, it would create this. This would be a different set, a different rule than the one on the last one I showed. But you'll see whether this is alpha this way, or I draw a horizontal line here and make it alpha this way, and rotate it, it'll make the same shape. And that's why there's two rulings. It's a double ruled surface. Okay, and so basically you can see here that the illusion here is that this is a hyperbola shape. It's bent, and yet this is a straight line, and yet it never collides, so you're able to sweep a straight line through it. This was a thing in Boston's Museum of Science. They had the central thing up here and the bar out and the straight thing, and it would go through the two hyperboloids, and then they had the thing on the side, and you can kind of see me in the back there looking in there. I'm back in a former life. So here we can see it with its two sets. Okay, so like I said, one set could be created. If you have some alpha and some L and you rotate around. The other set could be created if you have the same L and you angle it. If you draw the horizontal line this way and draw the same alpha that way, rotate. It doesn't matter the direction you rotate. Obviously, you'll fill basically the same shape. And it's a double ruled surface because anywhere I point, there's a point on there where it will be the intersection of two lines, and those lines make up the whole surface. So the whole surface can be filled with straight lines, no curves, nothing, and any point is the intersection of two lines. Okay, and so that's and of course. So this is the other, there's really only three surfaces that are double ruled surfaces, and that's the hyperbolic paraboloid, the two different kinds, of course, and hyperboloids, circular and elliptical. Those count for one. I guess I'm counting in those. But then the third kind of a double ruled surface is a plane, right? But planes are actually more than double ruled. They have any point. You can have many lines on them that intersect it, and they're also a minimal surface as well. Planes are. Remember, like I said, there's a minimal surface kind of version of a hyperbolic paraboloid that's the soap bubble, and it's approximately the same shape, but it's not mathematically identical. It's much more complex. But for the plane, the minimal surface and the double ruled surface of the plane, like those are of course the same. A plane's a plane. Okay, but a circular hyperboloid or an elliptical hyperboloid, it's a double ruled. It's the third type of double ruled surface here, and as a consequence, it's not a surprise that one set would be the freedom lines or the rotation lines, and the other set would be the blue pure force constraint lines. And the really crazy thing is, well, okay, even though it's a double ruled surface, does each set satisfy the rule of complementary patterns? In other words, if you look at every single blue line, does it really intersect every red line in the whole circular hyperboloid somewhere at least once? I mean, it's clear this one intersects there, this one intersects there, this one intersects there, this one. But what about the other side, right? Because there's red lines on the other side. And yes, the answer is if you go all the way up or all the way down, you'll find it will intersect one of these somewhere along any blue line. But when you get to the back, you'll see the red line will be parallel to this blue line, will intersect at infinity. So if I take any blue line, it will intersect every single red line somewhere in finite space except the one on the exact opposite side that's parallel to it and therefore intersects it at infinity. Okay, so it's kind of cool. But yeah, not only is it a double ruled surface, but they all satisfy the rule of complementary patterns. And so this is indeed the freedom space, that's the constraint space. And again, whichever way, it's not like all freedom spaces have this angle and all constraint spaces have this angle. This could be red and this could be blue. It's just whatever the red and the blue are, they're opposite. One's one set and one's the other set. And that's always the case. But they can be, L can, from this example, freedom spaces can have an alpha of greater than 90 degrees and also less than 90 degrees, and vice versa for constraint space. So they just have to be opposite. Okay, so you can see these are also a freedom constraint space type in the fact chart, but that's not just, and also remember you memorized circular hyperboloids have three things in it, which you know from here. 3 DOFs, 3 minus 3 is 3, and same thing here. You say there's three things in there, and hopefully you memorize that from that previous slide. But the point is there's not just this type. Circular hyperboloids are a fundamental subspace that one of the 12 building blocks that finds itself all over the chart. So there's a bunch of nested ones inside here. There's elliptical ones nested inside here. There's circular hyperboloids in this one. And you find them all over the chart as well, just like the hyperbolic paraboloids. So just like you find disks and parallel planes and spheres all over the place in the chart, you find all these. They're not just isolated freedom and constraint spaces. And you'll see that. Okay, so and also they're also used in architecture for many of the same reasons. you know, first of all, they're cosmetic. They're aesthetically pretty to make for towers holding heavy things up. You know, so they look cooler than just a boring cylinder. But they're also stronger. They're superior structurally. They're kind of like trussed with angles, but the loads are going through straight lines. And you know, there's two rulings that can make the nice surface, but hold up the weight along a straight line. But it's also you don't have to make custom bent pieces to get your cool shapes. You just make all straight beams and assemble them right, and then you get the illusion of the curves and those shapes and stuff. So they, you know, they're in water towers. They're in all kinds of things. This is a museum in St. Louis, Missouri, and then another really neat thing is they make for really great water towers, cooling water towers, and you know, nuclear power plants or other places. You know, they first of all they're prettier, right? Than it's just a cylinder, like I said. But it's a great way to structurally hold things up. But there's also some utility in the shape, in that it helps the water condense with a big area here, and then it kind of squeezes it up so it can kind of accelerate its way up and then condense as it comes out, so it become turbulent as it speeds up. So there's some physical optimization or there's some advantage to this shape for water cooling as well, and not just structurally. Okay, and you know, there's these things. You know, of course, they can hold fruit as well. That's kind of a trivial thought there, but you know, they're used in furniture and architecture because they're kind of pretty. They can also be used as you know, insertion pin things to make electrical contact. So they're kind of tight. When you push it in, they're definitely going to be squeezing against it to make nice electrical contact. This is you know, there's actually a great Vsauce video about this. I just actually discovered this morning. And he also found this Neolid Twiz, you know, thing that this water bottle that you can. It's got basically the two rings, and then there's kind of like fabric that's like the strings, and you can twist it and open it, and then you can twist it and make this seal tight thing, so you can hold it upside down and no water will come out. It actually makes a really tight seal as you twist those circles and pinch things off like a cone. It's just the cone is really shallow here. And then another really interesting thing is, you know, sometimes you want, you know, most traditional gears like spur gears just transfer rotational power along one axis to another parallel axis. But sometimes you want axes to be going in different directions. Of course, bevel gears can make them be intersecting. But there's a variety of other kinds of gears that can make them skew. And you know, usually people do skew orthogonal. But if you want any other angle, then the optimal shape to make your gears, put your gear teeth, are two mating circular hyperboloids. They can get skew axes at different weird skew angles. So they have some interesting utility in all kinds of things. The circular hyperboloid is not to be confused with the catenoid. This is another thing people confuse a lot. In fact, I think I've even seen in some science museums they get it confused. They might actually say that this surface is a circular hyperboloid. It's not. It's very, very similar to what I told you about the soap film, the bubble being the minimal surface that approximates a hyperbolic paraboloid. It's the same kind of thing. If you take two rings and dip them in soap, it'll make a catenoid, which, as you can see, looks like a circular hyperboloid, but it's not. It's the minimal surface that satisfies the condition of minimal surface geometries, and its sidewall here is actually a catenary curve, which is basically the cosh function, the hyperbolic cosine, a slight variation on it, and it's basically the shape that anything under its weight will hang with. So if you take a chain and hang it, it'll naturally form a catenary curve, and they tend to be great in architecture. So this is the St. Louis, Missouri, you know, famous arch is like a mathematically, you know, is close to perfect catenary kind of curve there. So it shows up in architecture and all kinds of interesting things, but it's not and if you take this shape, I didn't tell you, if you take this shape and rotate around its axis, like that's the shape you rotate around its axis, you'll make a catenoid. But like I said, catenoids aren't ruled surfaces. They can't be made with perfect straight lines like circular hyperboloids. They're the minimal surface that, given bounds, minimizes the surface area. And it's approximate, but it's not mathematically exact. This is a catenary on the side instead of a hyperbola. There's two kinds, right, of circular hyperboloids, of hyperboloids. There's circular ones and elliptical ones, and you can see the difference. It's very obvious. There's still, elliptical ones are a double ruled surface. They're a kind of hyperboloid, and yet the cross section going all the way up are ellipses. So the circle is a special condition of the ellipse. Okay, and you can see elliptical ones are all over these shapes too. Here's the freedom constraint space of this one, but you can see there's a bunch of screw spaces that are elliptical hyperboloids, and this one's nested elliptical hyperboloids. And anyways, they show up all over in interesting ways within either the red and blue or within the green of the freedom constraint space. Okay, so let's. So now it brings us to our final kind of complex shape that you need to understand. And by the way, all these shapes, if you want to know the math, there are mathematical equations that describe these shapes exactly, precisely. I'm just giving you kind of a qualitative understanding of their shape and how they work. But if you look at my master's thesis or even Wikipedia or just really anywhere, these are ancient shapes that have been well understood for a long time. But my master's thesis is probably the best way to read about these shapes in the context of fact, obviously, and these shapes as they relate to screw theory and stuff. The last shape is a cylindroid, or also called sometimes Plücker's conoid. Remember, Plücker is the guy that came up with the vector form for twists and wrenches. Some 3x1 vector on top, and then another 3x1 vector cross that, plus some scalar times that vector again. That form is a Plücker vector. He came up with this shape, and it's no wonder because this is a linear combination of two kind of Plücker vectors for this shape. Really what it is so first of all, you have to understand the shape can fit in kind of a cylinder. It has a finite height. It ends at some top and has a cap at the bottom. Of course, it's a ruled surface. It's made of lines. Okay, so let's see if I can show you this. Let's use my two fingers. If you put your two fingers on top of each other, and as I pull down, they kind of scissor out until they close together, like this. So as I move forward, and if I do it this orientation, it's like my two fingers when they overlap are here. When they end, my two fingers are going to overlap here, and there's a part in the middle where they're 90 degrees apart. So they kind of start here, rotate down to the 90 degrees, and then go down like that. Okay, so it's like there's an axis here down the center of this kind of cylinder, and at the top there's just one line, and at the bottom there's just one line, but then every point down here there's two lines that intersect it, and they of course go out forever, but if you bound them in this cylinder with this finite height and draw this, you kind of get this sinusoidal kind of Pringle chip looking shape, which I imagine is why they call it a cylindroid. Because when it's in the cylinder, it has this sinusoidal kind of shape. This is a drawing of it in MATLAB that they just hollowed out the center, but don't let it confuse you. Like it would have, they just hollowed it out so you could see the other side. But imagine it all filled together, and these lines are going through. So it's obviously a ruled surface because every part of it is defined by a line. Okay, but it's not a double ruled surface because there's really only these points along the axis and not the top and the bottom, will you find that they're the intersection of two lines. Every other point on this surface, only has one line going through it. Okay. Okay, so let me break it down a little more clearly. So, okay, and define some things. So the top line that only has one line is one of the extreme generators. Okay, and no surprise, the bottom one's going to be another extreme generator. Okay, but then once this, and this is looking down z-axis, you'll see right in the middle of the. So this is, like I said, there's a certain height to the cylinder, and right in the middle is the coordinate system. We're going to say, and x and y go out like this, and you'll see the extreme generator is always 45 degrees from that x and y coordinate system. Okay, if we align, z with the axis of the cylindroid, right? And but then as you go down a different cross section, you see I did red, a different cross section. It corresponds to these blue ones. Kind of starts opening up till you go even further down. And then you get to the central plane, like, if this has a height of h, you go h divided by 2, halfway of the cylinder, and you're now down to where the coordinate system is. And these are called the principal generators. They're the ones that correspond with the x and y axis. So, of course, since x and y axes are always 90 degrees, they're always orthogonal to each other. Okay? And then you keep going down, and they kind of scissor together until you get to the second and final extreme generator at the bottom where there's just one line. Okay? Okay, so that's kind of how it looks. So, this is a little confusing because I'm using blue. This does not mean constraint lines. I'm just saying I'm coloring them so you can see the two extreme generators. And then the green ones, they're not screws. They're just principal generators. And so I'm just using a different color scheme here. Sorry for the confusion. But you'll notice both principal generators are 90 degrees and both extreme generators are always 90 degrees. So the extreme generators are always 90 degrees for any cylindroid. And same thing with the principal generators. And the principal generators are always halfway down. And they're always spaced 45 degrees. Okay? So that is that's how they always are. Okay, and cylindroids actually show up the most of anything. Okay, so there's the entire freedom space is dedicated to these. You can see there's 3 cylindroids, and the only thing that makes these different is this cylindroid's made of all screws, but it has 2 rotations in it. This cylindroid's made of all screws, but has just 1 rotation, and this one's made of just all screws. Okay, so it's kind of interesting, and even though they basically look exactly the same, but they just have differences in how many rotation lines they have in it, their constraint spaces look completely different. So they're totally different things. Okay, and they'll appear to move pretty differently too. So, and of course, they're not just in those 3. Like for instance, if you take this one and rotate it around its principal axis, it actually makes this one. If you take this guy with 2 red rotation lines in it, and then you take its principal axis and spin it, it'll make this circular hyperboloid and give all the screws in its freedom space. And there's if you stack them next to each other, there'll be this freedom space here, type 6, 3DF type 6. So cylindroids are kind of the most prevalent. They're the hardest to see in there, but once you understand them, you'll see they're all over the chart. Okay? All right. And by the way, just as a future thing, you'll find in a future lecture, each of these columns is really just different manifestations of the same shape. And a cylindroid is basically all the freedom spaces in 2DOF column are basically different manifestations of a cylindroid, whether they're collapsed or stretched infinitely long, or how they're positioned or how they're displaced to infinity. You'll see there it's kind of all, just to make the chart even more beautiful, that they're basically just one and the same shape, different manifestations with different parameters, transforming into different looking things. So, but that's just it. So cylindroids are super important, especially a 2DOF column. But like I said, they're all over the chart. Okay, so all right. So with that. Let's see. Okay, so now we'll get into screw motions here. Let me get this bag here. And so while I'm building this here, I want you to look at this example. And it says, according to Maxwell's equation, remember 6 minus c equals r, how many degrees of freedom does this Flexure system have? Okay. Well, first of all, look at it and you'll see, is it a parallel serial system? Well, it's obviously parallel. The whole first half of this course is dedicated entirely to parallel. Okay. So it's got two rigid bodies and they're connected directly to each other. Okay. And then, let's see, and then there's, and then, according to Maxwell's equation, how many degrees of freedom does this Flexure system have? So, right, so what you can do is you can count the wires, and you'll see there's 5 of them. You see I've drawn, on the left side, you see one way you could assemble it and fabricate it. But on the right side, I'm drawing the blue lines through it. And so you can say, okay, 6 minus 5 wires is 1. Okay, so there should be 1 degree of freedom. Well, the question is, can you find what that 1 degree of freedom is? Okay, so either visualize it, stare at that for a little bit, put me on pause and see if you can visualize how that 1 degree of freedom would work. Okay, and then, if you can't visualize that, then what you can do is try and find the rule of complementary patterns and find the red line. It's just 1 degree of freedom because 6 minus 5. And I'll tell you, okay, it could be over constraint. So the right way to say it is 6 minus 5 is the minimum number of degrees of freedom there could be. Right? There could be more if some are redundant. But I'm telling you, those are non-redundant. They're all that is an exactly constrained parallel system. And so find the red line that intersects all those somewhere at least once. Okay? And you can put me on pause or keep me going and think about it. I'm actually quickly going to build this. Okay. Okay, so could you find the could you find the degree of freedom? Can you visualize how it moves? That would be pretty tricky. You'd have to be nearly a genius to be able to do that. Okay, but then the other question is, have you been able to find a red line that intersects all those lines somewhere at least once? Okay, well, most people, let's see if I can get this here. Okay, most people say, well, okay, what about a red line that intersects that point and that point, that goes through there? And it's like, well, okay, it intersects that one there, intersects that one there, intersects that one there, intersects that one there. But what about this guy? Somebody will say, well, what about a hoop? Well, no, it's clearly skewed to that red line, so that blue line will never intersect that red line anywhere at any time. Okay, so then that's not right. So can you find another red line? That's the most common one most students point out. And the answer is, no, you can't. There actually is no red line. There's not a rotation, and there's not even a red hoop that works because there's no parallel planes that all the blue lines lie on that would intersect at a hoop. So and if you think of drawing the disk of translation arrows perpendicular to all those axes, there's no common arrow that points in any direction. So that's the other way to find translations, right? I taught you that you get a disk of arrows that are perpendicular to these, and then you think of all those 5, which direction is common, and there is none. Okay, so there's no translation apparently, and there's no rotation. So again, you ask yourself, you might think, well, my goodness, is Maxwell wrong? Because his equation, 6 minus 5 non-redundant degrees of constraints has to equal the number of degrees of freedom. But, according to this, there's no translations or rotations, it's 0, so is he wrong? And the answer is, of course, always he's never wrong. There is a degree of freedom. So those are non-redundant. 6 minus 5 does equal 1, but what is that 1 degree of freedom? Well, what you do is build this with your Flexure kit, which I just did here. Okay. And let's see if I did that right. Yeah. So here, as you can see, here's the angled beams, the two in the back. Here's the two